Okay, we're going to look at the warm-up on graphing and writing polynomial functions. First question says a sixth degree polynomial function, f, only has zeros of 3, 2i, and negative 2i. Function bounces off the x-axis at the point 3, 0, and we're also given f of 4 is equal to negative 20. Write two possible functions that could represent this polynomial. So first of all, if we're a sixth degree polynomial, that means in theory, the fundamental theorem of algebra says we're supposed to have 6 zeros. But that's if we count multiplicities. Okay, so that means from our zeros given here, we have x equals 3, x equals 2i, and x equals negative 2i. That's 3 zeros, and we need to get to 6. So I could add a multiplicity here, and I could say, let's put another 3, another 3, another 3. And now I have 1, 2, 3, 4, 5, 6 zeros, but one of those zeros has a multiplicity of 4. That works because if I want to bounce off this x-axis at the point 3, 0, I need to have an even multiplicity of x equals 3. And so if I were to graph this, or actually we don't even need to graph it, but if I were, I might have some sort of function that just bounces off the point 3, 0, and we would be fine. The other zeros are going to be imaginary, x equals 2i and negative 2i. So if I want to put this function together, I can say f of x is going to be equal to, put an a value out in front because we don't know what the stretch or shrink of this polynomial might be. If I call my multiplicity at x equals 3, 4, I could write it 4 times, right? I could keep writing this out. Or I could really condense it and just write x minus 3 all to the 4th power. But that gets me to the 4th degree. I need to get to 6th. So the other question is, what do I do with these 2i and negative 2i? And the answer is I have to think about what would produce that, right? What would my factor be here such that when I use the zero product property and I say 0 is equal to this factor, my solutions come out to be, right, here's somehow x is involved in the factor, and I'm going to get x equals plus or minus 2i. Well, we get I when we take the square root of a negative. So I can think backwards and say, well, I must have taken x equal to be the square root, the plus or minus the square root of negative 4, because that would lead me to 2i. The square root of 4 is 2, and the square root of negative 4 is 2i. Working backwards even further, that would mean that x squared is supposed to be negative 4, or x squared plus 4 equals 0. So here, back with my zero product property, I could say, oh, here I had x squared plus 4. X squared plus 4, x squared plus 4. So now I'm almost done writing my polynomial, but I'm given one more piece of criteria, which is that f of 4 is negative 20, meaning when I plug in 4 to my polynomial, I'm supposed to get out negative 20 as my result. Okay, I'm going to erase and write some new lines here just to clean things up. So if I erase this, okay, I could say negative 20 equals a times 4 minus 3 to the 4th power, and then x squared, we said x was 4, 4 squared plus 4. Condensing down, we get negative 20 is equal to a, 4 minus 3 is 1 to the 4th, times 4 squared is 16 plus 4. I get negative 20 is equal to a times 1 times 20, or a times 20, or just 20a. So a must be equal to negative 1. Putting it all back together, one option for my function is f of x is equal to negative 1 x minus 3 to the 4th power x squared plus 4. So this is one possible solution here. The second possible solution is going to be if, and let me take all of this, get rid of it. It's going to be if instead of a multiplicity of 4, maybe we bounce off the x-axis at x equals 3 with a multiplicity of 2, And then maybe we have a multiplicity of 2 with our imaginary powers. So they're not even on the real, the graph of our real outputs, but maybe we have a multiplicity in a second copy of the i's. So what would this look like? Well, we already determined that this plus or minus 2i must have come from x squared plus 4 being a factor. And so if we have a multiplicity of 2, that means another factor of x squared plus 4 might exist, or I could write it as x squared plus 4 squared. Either way would be fine. And so when I put my function together, I would say f of x is equal to a x minus 3 squared from the multiplicity of 2 for that 0 of x equals 3. Then I'm going to put x squared plus 4 and maybe another x squared plus 4. Maybe I choose to write it this way. Okay. Then I still have this criteria that f of 4 has to be equal to negative 20. When I plug in 4 for x, I'm supposed to get out negative 20 for y. So let's try to solve that. Okay. So this time, if I plug in 4 for x, again, I'm going to get 4 minus 3 is 1, squared is just 1. 4 squared plus 4, where you said that was 20, and 4 squared plus 4 is another 20. So I'm going to end up with negative 20 is equal to a times 1 times 20 times 20. Doing all that out, we get negative 20 is equal to 400a, and then a is going to be equal to negative 20 over 400, which is equal to negative 1/20. So putting this all together for my second option for my function, I would end up with f of x is equal to negative 1/20 times x minus 3 squared times x squared plus 4. And this time, just because I'm running out of space, I'm going to write squared. Okay. So those are my two possibilities. I have to get to a 6th degree, meaning I have to have 6 zeros. The x equals 3, or the 0, 3, 0, that x-intercept has to have a multiplicity that is even. So it either can be this multiplicity of 2, or we could have had 2 more and got rid of these, or we can double up our imaginary multiplicity. So that's how we're going to answer this first question. Okay, moving on to our graph questions. To graph the function, we want to think about some key features. First thing is we want to look at the degree and the leading coefficient. So for the degree, you really want to be in standard form. However, this is going to take a little while to multiply out. And thinking about what's going to happen, I can see that this x, oops, how did that happen? This x term is going to get multiplied by this x term and this x term. And we have 2 copies of the first one, 3 copies of the second one. So altogether, we're going to end up with x to the 6th power when we multiply all these out. And then all of those x's are just x, and out in front we have a leading coefficient of negative 2. So we're going to end up with negative 2x squared as our first term, or sorry, negative 2x to the 6th power as our first term. And then I don't know what else comes next, but I can reason that that's my leading term. So my leading coefficient is negative 2, telling me that this function is negative. My degree is 6, telling me that's an even power. So I know that I'm going to look maybe something like this, or maybe like this. It's just an even function facing downwards. Another thing I can get is what is the x-intercepts, okay? Because those are some key points we need to capture. And so the first one is going to be at negative 2, 0, but because I have x plus 2 squared, that means I'm going to have a multiplicity of 2, and that we are going to bounce off this axis at this point. At x minus 1, giving us a 0 of 1, 0, I have a multiplicity of 3, which means we're kind of going to snake through the axis a little bit at that point. And then at x equals 4, or 4, 0, we have a multiplicity of 1, so we just cross the axis at that point. So I'll plot those down. We have negative 2, 0, we have 1, 0, we have 1, 2, 3, 4, 0. Those are my x-intercepts. I know my graph at some point is going to finish facing down and facing down. And now I just need to connect it. But one more thing I can figure out is the y-intercept. So if I have 2, -1, and -4 as my constant terms, -1 is being cubed, 2 is being squared, and we have a -2 out in front. And it's not that those exponents apply down directly, it's just that the constant term is going to be made up of that in the end. So I'll end up with -2 times 2 times 2 times -1 times -1 times -1 times -4. Okay, this all turns positive. This will be negative. So my answer is negative. 2 times 2 times 2 is 8. 1 times 1 is 1. And then 8 times 4 is 32. So the whole thing turns into -32. And we said that's going to be our constant term, or that's going to be our y-intercept. So let's just pretend my graph scales by 8s. So 4, or 8, 16, 24. Pretend that's 32 down there. All right, now I just need to piece it together. So we said at my 0 of -2, 0, I need to bounce. So I'm going to come up to this 0, bounce off of it. At some point I'm going to need to go through that y-intercept. So maybe I'll come at it and come back up through it. We don't really know, and we don't really need to be that specific. We're just getting a rough sketch here. Oops. Okay. At 1, 0, we are supposed to snake through. So I'm kind of cramped on my graph. I guess I can zoom in a little bit. This really just means I need to sort of come in a little bit smooth and snake through a little bit. It's kind of hard to do on a small graph. Let's try one more time. So if I smooth this initial curve, bounce here, go smooth, kind of snake on through there. That's not really a great drawing of it, but you get the idea. And then our last one, we're going to have to turn around and cross through. So this is a pretty poorly drawn graph, but it captures the main idea of this function. And if you were to graph this in Desmos, it follows this general shape. The whole point of this is just helping us to get the general shape of a function, even though it might not be that pretty. Okay, and then this last one is very interesting. So let's try to erase all this. Okay, so first of all, I have x to the first, and we have a cubic, and then another cube. So this is going to be a degree 7 polynomial. My first term is going to end up being 1/3 x to the 7th when it's all multiplied out. Don't know what comes after. My constant term is going to be -1 cubed times -1 times 1/3, which is going to be 1/3. So my y-intercept is going to be at 0, 1/3. Leading coefficient is 1/3. Degree is 7. So that tells me a good bit of information. It tells me it's an odd function, so it kind of looks maybe like this with the end behavior. It's positive. We have a y-intercept. Our x-intercepts are other key features. We have 1 at 0, so we're going to cross at this point. We have 1, 0, which has a multiplicity of 3, meaning we kind of snake a little bit. And then at x cubed minus 1, this is a little weird. But this is a 0 with a multiplicity of 1. And then there's also 2 imaginary zeros contained in there. And so I'm going to graph this, and I'm going to show you what I mean by that, because this is pretty weird and complicated. It won't be on your quiz, but it's interesting to look at. So if we graph this function, y-intercept at 0 and 1/3, let's just pretend this is 0, 1/3. Let's say each of those tick marks on the y-axis scales by 1/3. Then we have x-intercept at 0, 0. Ooh, I was wrong. That's very interesting. So that means my y-intercept is at 0, 0. I neglected to notice that this x term, x plus 0, is going to make my constant term actually 0. Whoops. So if you caught that, my apologies. And if not, well, now you can see what it's like to notice something was wrong. Because I noticed that my y-intercept can't be different than my x-intercept if it's at 0, 0, because the function's only allowed to cross the y-axis or have an x-coordinate of 0 once. All right, I'm going to put 1, 0, and that has a multiplicity of 1, but it also has a multiplicity of 1 from here. So there's a multiplicity, like there's 1, 0 from here, then there's 1, 0 from here 3 times. So really it has a multiplicity of 4. So I think we're going to bounce off the axis at this point. Really weird. So we'll come like this. We'll bounce. Okay. Well, all right, let's graph this function to make sure what we've done is accurate. So I'm going to pop over to Desmos. Let's see, 1/3 x minus 1. Okay, some other graph. And let's type this in. 1/3 times x times x minus 1 cubed times x cubed minus 1. All right, so we basically captured what we wanted to, right? We bounce off the graph at that point 1, 0. Our y-intercept 0, 0. We did a pretty good job capturing this. When we come back to our graph, yeah, that looks pretty good. The only thing, though, is this accounts for, here's 1, 0 here, right? That had a multiplicity of 1. This, I guess, has a multiplicity of 4. But we said the function had a degree. Ooh, what just happened? Well, need a new update, I guess. Alrighty, let's try this. Come on, Notability, let's not be difficult. Okay, so that had a multiplicity of 4. But we're supposed to end up with 7 zeros. So here's 1, here's 4 more. That means we're missing 2 zeros, which is fine. They must be on the complex plane, or they must be imaginary zeros. If we look at our function, 1/3 x minus 1 cubed, and x cubed minus 1, and we apply the zero product property, well, this one's going to just be x equals 0. This is x minus 1 equals 0, and just doing it 3 times. So like we keep getting x equal 1, x equal 1, x equal 1. This one is weird. So we have x cubed minus 1 equals 0. And you might think, oh, that's all good and well. But if we're considering the complex plane, and we saw when we get x cubed equals 1, x is equal to the cube root of 1. And we say, well, cube root of 1 is just 1, right? And it is. So we get this extra multiplicity. We get another x equal 1. And there's 4, there's 1. That's 5 zeros. But over the complex plane, the cube root is a little bit more complicated, which I'm going to show you just to see. If I draw my complex plane, over here is 1. Here is -1. Here's I, and here is -I. And we can think of multiplication on the complex plane as being rotations, okay? So if I want to say x cubed equals 1, or x is the cube root of 1, a way of saying this is, how can I rotate three times and get back to 1? The first answer would be just 1 full rotation. So this rotation represents 1. And then we do it again, 2, so that's times 1. And then 3 times 1. 1 times 1 times 1 is 1. So that's our solution that we just found a second ago, x equal 1. But there are other ways we could get back to the starting point of 1. We can get back to right here even without going all the way around 3 times. For example, if I drew in a little line here, and I said, what if we did 120 degrees? And if I broke that up and I did 120 degrees, and then I went another 120 degrees, so say I get to pretend this is 240 degrees from the start, and then all the way back around is 360, and that gets me right back to 1. So it looks like whatever this is works, and it does work. That's also going to be a cube root. And the math behind that's a little interesting. We take cosine of theta, which in this case is 120, plus I sine of theta to figure out the number. You kind of need pre-calc for that to make any sense. So we'll say cosine of 120 plus I sine of 120. Cosine of 120 happens to be, I want to say it's negative 1/2. And sine of 120, I believe, is square root 3 over 2. Okay, so this is also one of our zeros. And so it may look really weird, but we're basically saying that that cubed equals 1. So if we include imaginary solutions, that's also a cube root of 1, or if we cube it, we get 1. If we want to take a look and expand this and confirm, well, we could say, and just sort of do this out and do the distribution, negative 1/2 plus I square root 3 over 2 times negative 1/2 plus I root 3 over 2. Do it one more time. And we can just do the distribution, and we'll eventually get there. But I think this is a great opportunity to use Pascal's triangle. So if I have a plus b to some power, a binomial expansion, I can use this Pascal's triangle to figure out the coefficients of this binomial expansion. In this case, we're raising it to the third power. So I need to go to this fourth row, because this is to the 0 power, to the first power, squared, cubed, right? And to the 0, 1, 2, 3. Here's my triangle. So I need this row. I'm going to end up with a plus b cubed expanding to a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, in this case, a is given by negative 1/2. B is given by I square root 3 over 2. So if I expand this, a cubed is negative 1/2 cubed. 3a squared, well, a was negative 1/2. B is I square root 3 over 2. Then 3a is negative 1/2. B squared is I root 3 over 2 squared. And then our final part is b cubed, I root 3 over 2 cubed. Working down, negative 1/2 to the third power is going to be negative 1 over 8. Negative 1/2 is squared is going to be positive 1/4. And then I root 3 over 2. Here I'm going to end up with 3I root 3 over 8, so I'm going to write my next line here, plus 3I root 3 over 8, just multiplying my numerators and denominators. This next piece is 3 times negative 1/2. Then we're squaring this, so we end up with I squared, and root 3 squared is just 3, all over 4. Simplifying down, we end up with negative 3/2, or negative 9 over 8. Let's do it this way. Negative 9 over 8, I squared. But I squared is negative 1, so we end up with negative 9 times negative 1. And if we do negative 9 times negative 1, we get positive 9. Now this should be interesting, because let's say I combine these two terms, I'm going to get 8/8, aka 1. The goal is to get 1. And note that this other piece here is imaginary at the moment, and I still have one term left. So if we get those to combine, we'd expect maybe the imaginary parts will cancel. So let's take a look. Here in our last part, with I root 3 cubed over 2, or I root 3 over 2 cubed, we're going to end up with I cubed. Root 3 cubed is 3 root 3. All over 2 cubed is 8. Okay? Now here's where the magic's going to happen. I cubed is equal to negative I. So substituting in negative I for I cubed, I get negative I times 3 root 3, which is most often written as negative 3I root 3 over 8. Combine that with positive 3I root 3 over 8, and we get 0. So we get 1 plus 0 equals 1. So we do find that when we actually do out this math here, negative 1/2 plus I root 3 over 2 cubed is equal to 1. Very interesting. So that gets us one more 0. Then there's another 0, but we're not going to find that. You would use somewhat similar of a process. You try to figure out what other angle could we multiply by 3 to get us back to 1, but that's really not in our Algebra 2 realm. That's more pre-calc. But I think it's kind of cool to see how this all comes together, and it's a little unbelievable that this wild equation, right, or this wild number really, negative 1/2 plus I square root 3 over 2, came from 120 degrees because it's a third of 360 and we want a cube root. Somehow that gets us 1 plus 0 or just 1 when we cube it. It's pretty wild that that all comes together. So it's very, very cool. A little bit above what we need to worry about at the moment, but figured I would show you. So hopefully this was interesting. Hope you enjoyed the video.